Number 1, solve the equation 27 to the x equals 9 to the x minus 3, 4x. So I have two exponential expressions on both sides here, so I'm going to try to get common bases. Are 27 and 9, are those related somehow? They are, because 27 is 3 cubed, and 9 is 3 squared, so I can get them to have a common base. So I can rewrite 27 as 3 cubed raised to the x equals 3 squared to the x minus 3. And now I have a power to a power, so I can apply that exponent property and multiply them, and be careful and make sure you remember to distribute or include parentheses there. So now that I have a common base, exponential functions, if they have the common base and are equal, their exponents must be equal. So 3x has to equal 2 times x minus 3. And that's a nice linear equation that we know and love how to solve. And we get x equals -6. What's nice about exponential equations is we don't need to check them. We know that if we get x equals -6, that is the solution. So our process for solving these exponential equations right now is see if we can get a common base on both sides, apply the power to a power property, and set the exponents equal. Number 2, solve 5 to the 4x equals 125 to the x minus 1 algebraically for x. So how are 5 and 125 related? Well, there's nothing I can do to 5, but I can rewrite 125 as 5 cubed. 5 cubed is 125. Applying the power to a power property, we get 3x minus 3. I'll distribute right now. Now that my bases are equal, I set the numerators, not the numerators, I set the exponents equal, and solve for x. These first two have been very nice, and we get x equals -3. We can always check these if we wanted to by plugging x back in and using our calculator to see if we get the same expression on both sides, and we will. Solve this equation. All right, 2 to the x squared minus 3x equals 1/4. Now it doesn't look like this is an exponential expression over here, but 1/4, well, that's 2 to the -2. So using that idea, we can simplify this and make it so that we can use the method of common bases to solve this. So it's recognizing that 1/4 is really 2 to the -2. Well, 4 is 2 squared. Because it's in the denominator, it's 2 to the -2. So I set the numerators, not the numerators, I'm going to say that all the time. I'm going to set the exponents equal, and we end up getting a quadratic here. And we know to solve a quadratic, chances are we're going to use the zero product property, which means it needs to be set equal to 0, and it needs to be factored before we can use the ZPP. X minus 1, x minus 2. Those multiply to 2, that adds to -3. And we get x equals 1 and x equals 2. We have two solutions now because we ended up with a quadratic. So sometimes we can end up with quadratic equations. We can end up with really any polynomial equation. We can end up with anything after we set our exponents equal to each other. But we just need to solve that equation somehow, and hopefully we have the tools. Number 4, solve this equation by using common bases and the properties of exponents. So looking at this, I have a 3, a 243, and a 9. What are all of those related to? Hopefully 3. I know 9 is 3 squared. 243, if you experiment around a little, you'll see that's 3 to the 5th. So I have 3 squared, 3 to the x squared, 3 to the x squared over 3 to the 5th raised to the x equals 3 squared cubed. Okay, let me use power to a power. Power to a power means multiply. 3 to the 5x equals 3 to the 6th. Now you might be saying, well, do I use power to a power up here? The answer is no, because I just have an x squared in the exponent. It's not 3 to the x squared. It's two different things. I'm saying I have 3, and inside my exponent I have x squared. So make sure you're not using power to a power in that numerator, because it's not set up that way. It's not 3x quantity squared. It's 3 with an x squared in the exponent. I have division between two things with the same base, so that means I can subtract the exponents. And look, I have common bases now, so I need to solve x squared minus 5x equals 6. That's a quadratic. Hopefully I'm going to set it equal to 0 and use the 0 product property. If I can't factor it, I'm going to have to use the quadratic formula. Luckily, we can factor this. Be careful, because it's 5 and 6. What multiplies to negative 6? That adds to negative 5. They have opposite signs, because they multiply to a negative number. I need a negative 6 and a positive 1. Multiplies to negative 6, adds to negative 5. We get x equals negative 1 and x equals 6. Those are our two solutions, x equals negative 1 and x equals 6. Those two values of x, if I plug them in, would make this equation true. And finally, number 5, consider the equation 5 to the x squared minus 16 equals 1. Solve this equation for all values of x. There's a couple ways of going about this. The most important thing is you need to somehow get a common base. But what's the common base between 5 and 1? Maybe you don't see that. So maybe you need to recognize 5 to what power gives me 1? 5 to the 0 power gives me 1. So I'm going to really rewrite 1 as 5 to the 0, because anything to the 0 power is 1. Now that I have a common base, I need to solve x squared minus 16 equals 0. So you could use this by using common bases, or you could think about it 5 to what power gives me 1? 5 to the 0 power gives me 1, so this x squared minus 16 has to equal 0. That's the difference of perfect squares. So we have x equals negative 4 and x equals 4. So our solutions are x equals plus or minus 4.